All right, so for this problem here, I wanted to go over Hess's law, which states that if you take a look at the individual steps to get the actual overall reaction, you could calculate what the entire enthalpy is going to be for the reaction. So we're looking for delta H of the reaction here. Okay, and one way we could do that is by taking a look at these different steps that we could use to get to the overall reaction. And we're going to have to do some manipulation of these equations here to figure out what the enthalpy of the reaction is going to look like. So remember, for the overall equation, you can't touch this. You can't multiply by anything. You can't flip it. This is what you're trying to aim for. So we're not going to do anything to that equation. You also want to work backwards to get an equation that looks something like this. So I'm just going to pick any element that I see in one of my equations here, and let's take a look at this guy right here, WO3. You could see that it's sitting over on the right side of the equation, and then when I see what my overall equation really looks like, I could see that it's on my left. So right away that I know that I'm going to have to probably flip this equation. So I'm going to go ahead and do that here and get it over on the left side. And then I have my 2 tungstens plus my 2 oxygens. And the delta H, we started off with a negative 1,685, but it's going to become positive 1,685.4 kilojoules here. Okay, so we have WO3 over on the left side, and that is what it is on the overall equation. But we also notice here that this guy here has a coefficient of 2, whereas in my overall equation it is just 1. So it's a coefficient of 1. So I know I need to go through and actually half everything, and that including my enthalpy for the step as well. So we're going to wind up with actually 3 halves O2, and we're going to take our 1,685.4 divided by 2 as well, and we're going to wind up with 842.7 kilojoules. And now I know that this equation is something that I don't need anymore. Okay, so let's check out my second equation. I have hydrogen here. I have 2 hydrogens, and I have 3 hydrogens in my overall equation. It looks like they're both on the correct side. They're both on the left. But again, your coefficients don't match. I have 2 over here, and I have 3 over here. So I'm going to check through to see if I have any other hydrogens located in the other equations, and I do not. So I know that this is the only way, or this is the only thing I have to manipulate to get it to 3. And if you take this entire thing and then multiply it by 1.5 or 3 halves, 3 halves times 2 will get you 3 hydrogens over here. And we're going to have to do the exact same thing for the enthalpy provided for us as well. I'm going to multiply it by 3 and then divide it by 2. So if we went through and I rewrote this equation to reflect this, 3 halves times 2 would be 1.5 times 2. So you just have 3 hydrogens, and we have 3 half oxygens. And then we have 3 times 2, 6 divided by 2, and that would give us 3 H2Os here. And likewise, I'm going to take the enthalpy for that step and times it by 1.5 or 3 halves. So we got negative 716.76 kilojoules. Okay, so looking at my overall equation, it looks like we have the right coefficients, we have everything where it needs to be. So our final step is we're just going to add it up and make sure that we do indeed end up with the overall equation here. So first thing I want to do is I want to take a look to see if anything is going to cancel out. And things, remember, will cancel out if you have them both on the left and the right side of our equation. So I have a 3 half O2 here, and I also have a 3 half O2 here, and that's on the product side. This is on the reactant side, so these guys just cancel out. Okay. And then if you check out what else we have, it looks like that is all that cancels, so we're ready to just add up. So I'm going to take everything on my reactant side, all this stuff which is to the left of the arrow, and then I have this which is on the product side to the right of the arrow. And you could see that our equation here does indeed match our overall equation, so we got what we needed. And finally, for the enthalpies for these two different steps, all we have to do is add it up. So I'm going to go 842.7 plus negative 716.76, and we wind up with a enthalpy for the reaction of 125.94, and don't forget your units of kilojoules over here. Okay. So I'm going to go ahead and do a bond energy problem as well. And let's see. I wanted to do a problem where you're going to be solving for an unknown bond energy. I think I remember seeing one on the back. Okay, so if you guys are checking out your homework packet, it's on page 4. And I'm checking out number 8 over here, the problem with oxygen difluoride. And I said that as a little trick. This one is a little bit of a trickier problem because you actually know the enthalpy for the overall reaction this time. It's given to us. It's negative 318 kilojoules. But what we don't know is we do not know the bond energy of the oxygen fluorine bond. So this right here is going to become an X. It's going to be an unknown for us. So before we get there, let's go through and kind of draw all this out. We have OF2, and we also have water. Okay, so our equation looks something like this. This one's a problem where it's a little bit easier to actually draw out the Lewis structures, but for some of them, if you don't know how many bonds are going to be formed, really good idea to actually do the math to calculate how many bonds and things that we're going to be needing to put in. So remember, the setup is this. We're going to take a look at all of the bond energies involved on the reactant side. And remember here that in order for a chemical reaction to occur where you have reactants and products, the reactant bonds actually have to be broken. So that bond, that bond, that bond, and that bond has to be broken. And we would say that to break bonds, it is going to be an endothermic process. If you guys remember endothermic versus exothermic, endothermic means that heat needs to be put in for this to be broken, okay? Whereas on the other side, where we're going to be forming new bonds, you take energy level, and we're going to actually decrease the state of energy by forming these new bonds as these atoms are going to become more stable. So energy is actually released from the reaction. So it's an exothermic reaction, okay? And in class, we talked about how if something is endothermic, it's a positive energy that goes in. And if something is exothermic, because energy is lost, it ends up becoming a negative number on that side. Okay, so let's go through the math now. We have 2 oxygen fluorine bonds. Okay, and we also have 2 oxygen hydrogen bonds. Okay, now all this information was given to us right over here. And you guys would get these numbers on the test as well, unless you're being asked to solve for one like we have for the oxygen fluorine. So if I'm looking here and I'm trying to figure out the bond energy between the oxygen fluorine bond, it's not given. And in fact, we remember from back here that it's something that we're trying to solve for. And because I have 2 of these OF bonds, this is not just going to be 1x, but it's going to be 2x. And then the 2 oxygen hydrogen bonds, it's one bond is 467. And we're going to multiply it by 2 since there are 2 of those bonds. And these guys are going to come out to 2x plus 467 times 2. And you would wind up at 934 right here on the left side. Okay. On the product side, you guys have 1 of these oxygen double bonds, and we have 2 of these hydrogen fluorine bonds. So oxygen double bond is 498. The hydrogen fluorine bond is 565 times 2. Okay, so we're going to go through and add them all up. 498 plus 565 times 2. And you wind up with 1,628 for this side here. Okay. Now, we're not through yet because, again, this time we know the total enthalpy for the reaction. It's negative 318 kilojoules. But what we do not know, or the unknown again, is that oxygen-fluorine bond energy right here. So let's set up an overall equation. We know that it's all the reactant stuff minus the product stuff. Okay? Or you could think of it as this is a positive energy because we know it's endothermic. This is a negative energy because it's exothermic, and then we just add the two together. Okay, so for setup, it's going to look like 2x plus 934 minus 1,628 is equal to my total enthalpy for the reaction, which is negative 318 kilojoules. Okay, so we're just going to go through and do the math to solve for the x. I have negative 318 plus 1628. Then I'm going to subtract 934 from that. And I wind up with 2x is equal to 376. Then to solve for x, I'm going to divide by 2. And then I figure out that x is equal to 188 kilojoules. And this is bond energy, so it's kilojoules per mole right here. So you guys could see that. And that would get to the end of our problem here for bond energy.